All right, so we're going to move ahead and move into Chapter 10. Chapter 10 is, it sort of feels like a little bit of a hodgepodge of a bunch of different topics, but they are connected. Um, and they're connected in ways that will become apparent as we move through the chapter. But we're going to be talking about a bunch of things here. So in Chapter 10, we'll talk about parametric equations, we'll talk about polar equations, we'll talk about conic sections, and then we'll talk about the connections between all of these things. So let's get started with parametric equations. So so the idea behind a parametric equation is that it's going to give us a way to describe motion in 2 dimensions. Okay, so up until now we've really only been working with motion in 1 dimension with respect to time, right? So in other words, whenever we were saying, a projectile is launched into the air and its distance from the ground at a particular time t is given by this function, by a particular function, right? Well, that function is only describing the distance of the particle from the ground, right? It's only describing the motion of the projectile in 1 dimension. But obviously, we live in a world where things move in 3 dimensions, right? And so, we'd like to have a way to deal with that kind of situation. And the way that we deal with it is we use what are called parametric equations. So the idea is this. Suppose a particle moves along a curve C in the xy plane in such a way that its x and y coordinates as a function of time are x equals f of t and y equals g of t. We call these, right, the x equals f of t and y equals g of t, we call these the parametric equations of motion for the particle. We call the curve C that the particle follows the trajectory of the particle. And then t, x equals f of t, y equals g of t. So t, that variable, that dummy variable, is called the parameter. As I said, this will give us a way to describe two-dimensional motion. In Calc 3, you'll talk about using parametric equations to to describe 3-dimensional motion. And as kind of crazy as this is to wrap your brain around, there are situations in which it's useful for us to deal with parametric equations with multiple variables, more than 3 even. And to some extent, I mean, you kind of see that in linear algebra too. But okay. So when we're graphing parametric equations, so this is something that's maybe a little bit confusing at first, but if we take a step back and think about like our 1-dimensional stuff that we have been doing thus far in calculus, whenever we graphed the 1-dimensional motion of a particle, we always graphed it with time along the x-axis and then the displacement along the y-axis. Well, when we graph parametric equations, we don't really graph time anymore. We just graph the outputs of the individual functions, right, along the x-axis and along the y-axis. And so the time dimension doesn't really show up in the graph except as an orientation, right? So t only shows up in the graph as an orientation. And I'll show you what that looks like as we look at an example. So let's look at this first example. It says, sketch the trajectory over the time interval 0 to 10 of the particle whose parametric equations are x equals t minus 3 sine t and y equals 4 minus 3 cosine t. And then indicate the orientation with arrows. Okay, so let's do that. For right now, we don't really have any good tools to work with in order to be able to do stuff like this, so we're just going to plot points, and that's fine. So plotting some points, we're going to plug in some values for t. So we'll plug in some stuff for t, and then we'll get outputs for x and y, right? X is t minus 3 sine t. And y is 4 minus 3 cosine t. So I'm just going to plug in, since these are good for any t between 0 and 10, I'm just going to plug in all of the whole numbers between 0 and 10 for t to see what I get for x and y. So 4, 5, 6, 7, 8, and I'm going to go off the page, but you can extrapolate, I think. Okay, and then I'm just going to use my calculator to fill this stuff in. Actually, let me move this up because you've seen the problem already, so you know what it is that we're dealing with. So let's just use our calculators and plug this in. So for x, I'm going to do well, I can do some of this in my head anyway, right? 0 minus 3 times 0 is just 0, right? Well, when I get to 1, I guess it's a little more difficult. But here, cosine 0 is 1, so this is 4 minus 3, which is 1. Okay, the rest of them, I am going to have to use my calculator. This should be in radians, right? It's in radians, okay? So make sure your calculator is in radian mode. We're going to do 1 minus 3 times sine of 1. That comes out to about negative 1.52. If I go back and plug in 2, I get about negative 0.73. If I plug in 3, I get about 2.58. Excuse me. If I plug in 4, 6.27. Okay, so you see how this is going, and I'm just going to pause the video, okay, and then come back with everything filled in. So give me a sec. Okay, so I've got them all filled in now. Okay, so I got all the x's, got all the y's, right? Y is obviously a different function, but you plug that into your calculator, and then you can plot these points, right? So let's see. For x, I need to go out to, looks like about 7.9. So we'll go up to 8. And then for y, it looks like I need to go up to about 7. Okay, so I'm just going to give myself a little axis system then. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. And then over here I'll go out to maybe negative 2 so that I can get all of my points on there. And then I'm just going to plot the points. Okay, so 0, 1, negative 1.5, 2.4. So obviously I'm not going to be able to get super accurate anyway. Negative 7.3 and 5.2, 1, 2, 3.4, 5. So something like that. 2.58, 2.5, 7. So that puts me about there. 6.27, 1, 2, 3, 4, 5, 6, and 6. 1, 2, 3, 4, 5, 6, and 6. 7.88 and 3.167. That's almost 8. And 3.1, 1, 2, 3.1, maybe right about there or so. 6.8. Oh, so that actually moves back a little. And then 1.1. 5. 1, 2, 3, 4, 5. 1.7. So that's a little higher. And then 5 again and 4.4. 1, 2, 3, 4.4. Maybe 1, 2, 3, 4. Should have labeled these. Would have made it easier. 4.4. And then 7.8. Oh, shoot. I needed to go out to 11. Well, 8, 9, 10, 11. Well, 11.6. Well, it's going to be off the page. But anyway. Okay. Where did I leave off? 7.8 and 6.7. 1, 2, 3, 4, 5, 6, 7.8, and 6.7 puts me all the way up. 1, 2, 3, 4, 5, 6.7, so all the way up here. Okay. So at this point it looks like just a bunch of dots on the page, but if I trace out kind of like the way that this happened, I started here and then I went up there, then up to there, and then down to here, and then down, and then back around, right? Up to there. And then the very last point is 11.6, 6.5. So 11.6, right? 6.5 is like maybe something like that. Okay. So it does this little spiral thing. And that's it. That's the graph, right? That's the graph. I said to indicate the orientation with arrows. So the orientation was this way, right? As t increased, this is the way that the particle went, right? Anyway, so that's the orientation. So again, notice that like t itself doesn't actually end up anywhere on the graph. We could, since we're only dealing with 2 dimensions, we could have a t-axis that comes out of the page, and then you could plot kind of in 3 coordinates. You could plot t that way, but we're just plotting the outputs themselves, the x and y coordinates, and this is what the motion ends up looking like, right? And t kind of shows up as this orientation. Anyway, so that's how that works. Now, obviously, this is kind of a tedious process. So if you can graph it by eliminating the parameter, if you can graph the trajectory by eliminating the parameter, then that's probably a slightly better thing to do, right? A slightly easier way to graph. And sometimes we can, right? Oftentimes we can. So let's practice doing that. So let's practice graphing some parametric curves by eliminating the parameter. So for part A, let's do this for x equals 2t minus 3, y equals 6t minus 7. Again, you could do this the same way we did example 1, but except that the instructions say to do it by eliminating the parameter. And if you can eliminate the parameter, it's really going to make your life a lot easier, because you don't have to sit there and fill in all of this stuff, right? So how do we eliminate the parameter? Well, what you can do is solve one of the equations for t, and then plug that expression into t in the other equation, right? So I'm going to take this first equation and solve it for t. So I would add 3 and then divide by 2. So I would get t equals 1/2 times x plus 3, right? I add the 3, and then I divide by 2, which is the same as multiplying by 1/2. Okay, so from this equation, I get t equals 1/2 times x plus 3. So now I can take that and plug it into this equation, right? I can plug it in there for t. And so I get y equals 6 times 1/2 times x plus 3 minus 7. 6 times 1/2 is 3. So I would have 3x plus 9. And then 9 minus 7 is 2. So I really have 3x plus 2 at the end of the day, right? Oh, so there you can see that this parametric equation that we've started off with is really just a line, right? It's a line with slope 3 and y-intercept 2. It almost feels insulting to even graph it, right? We're way beyond that at this level, but you know, whatever. We'll do it. I suppose. So, by the way, here we weren't given any restrictions on t. In the previous example, t was between 0 and 10. Here, t could be from negative infinity to positive infinity because no restriction was actually written. So, anyway. Oh yeah, okay. So, intercept is 2, slope is 3. 1, 2, 3 over 1. And boom, right? Something like that. 1, 2, 3 over 1. So, really, it doesn't cross right there. It really should be like you know. Anyway, but you get the point, right? It's just this straight line. As far as the orientation is concerned, to figure out that, I mean, for that, I think you do kind of just have to plug in value for, but just a couple values for t should be enough. Like if I plug in 0, I'm at the point -3, -7, so somewhere, you know, down here. And then if I plug in 1, I'm at the point -1, -1. So I go from somewhere way down here to this point right there. And so obviously I'm moving in this direction, right? The orientation's going like this. Okay. So let's do another one. Let's do x equals cosine t, y equals sine t, t between 0 and pi over 2. Or 0 and 2 pi, sorry. Okay, now this one's a little trickier because, well, if we tried to solve this equation for t, let's say, we could say t equals cosine inverse of x, but that's not quite right. That's only one solution. This should have infinitely many solutions. So one of the kind of sets of solution is that t equals cosine inverse of x, but then you have another solution every 2 pi units after that. I suppose since t is between 0 and 2 pi, you only get the one. But then there's a second solution, right? Because t could also be 2 pi minus cosine inverse of x, which is also going to be inside of this interval. And so you get two solutions. And so then you have two solutions that you have to plug both of them in here. And I don't know, it just gets messy because even then you're going to have like sine of cosine inverse of something, or sine of 2 pi minus cosine inverse of something. And then you have to do some like complicated trig, try to simplify that. I think a much better thing to do is to just try to be a little clever and to realize that, hey, if I square both of these equations, right, if x equals cosine t, then x squared equals cosine squared t. And if y equals sine t, then y squared equals sine squared t. Now, how does that help me? Well, because cosine squared plus sine squared is just 1. So I can say cosine squared t plus sine squared t equals 1. Right? That's just the Pythagorean identity. And then you say, well, but how does that help me? Right? Because I'm trying to eliminate the parameter. I'm trying to get an equation in terms of x and y. Well, it helps you because there's x squared and there's y squared, right? So this is just x squared plus y squared equals 1. And there you go, right? You've eliminated the parameter. This is just a circle centered at 0, 0 with radius 1. This is just the unit circle, right? Again, it's almost insulting to have to graph it. But, you know, there it is in all of its glory. Ooh, that was horrible. That was horrible. I need to work on drawing some circles, right? Anyway, but there it is. As far as the orientation is concerned, I mean, again, we could plug in, if we plug in 0, we get the point 1, 0. So we're starting here. And then if we plug in pi over 2, then we get 0 and 1, right? We get that point right there. So we're moving in this direction. We're moving in a counterclockwise orientation. Okay. Let me give you one more. That was kind of like the previous one, because those ones can, the ones where you have to do a little bit of trig, the ones where you have to do a little bit of trig can be a little, you have to be clever, right? You have to be clever. So let me give you another example to kind of help you out on some of the homework, hopefully. Well, let's say that you had something like this. And I'm not so worried necessarily about graphing this right now because it turns out that this thing is a conic section, and you should have experience with conic sections, but we haven't reviewed them in a while, so we're going to be reviewing them here in a couple of sections from now. And so when we do, we might come back to something like this. But But let's at least eliminate the parameter so that you can see how you might go about doing that. So we have a tangent and we have a secant. And based on the previous example, you might be thinking, Pythagorean identity. And if you are, then great, because that's really what you should be thinking. However, before you apply it, you need to isolate the trig function first. So in other words, like here I can take I can say that x over 2 equals tangent t, and then here I can say y minus 3 equals secant t, right? Then I can square both sides and say x squared over 4 equals tangent squared t, and y minus 3 squared equals secant squared t. And then to relate these two things together, you have to remember the Pythagorean identity. It's not true that tangent squared plus secant squared equals 1, but it is true that, what is it? Tangent squared minus secant squared equals 1, I think, or maybe the other way around. Actually, it's the other way around. Secant squared, it's secant squared minus tangent squared equals 1. Okay, it's a Pythagorean identity. So we can say, all right, secant squared t minus tangent squared t equals 1. Well, secant squared t is just y minus 3 squared. Tangent squared t is x squared over 4. Anyway, so this is a conic section. And if you can't tell what conic section it is, I'll let you know. This thing is a hyperbola centered at 0, 3. And yeah, so it's a hyperbola. Maybe we'll graph it. Yeah, so in fact, let's just graph it, right? So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Ooh, I should have given myself more space. And maybe some graph paper would have been nice, I suppose. But anyway, so it's centered at 0, 3. And then the way that I graph hyperbolas is I look at the thing I'm dividing x by. I take the square root of that. That tells me how far to move left and right. 1, 2, 1, 2, right? Because square root of 4 is 2. I look at the thing that I'm dividing my y group by, in this case 1. I take its square root. That tells me how far to move up and down. So in this case, square root of 1 is just 1. From that, I can draw a box. And through the box, I can draw the two diagonals. Those serve as the asymptotes for my hyperbola, right? If you've never seen this before, then I'm sorry for kind of throwing this all at you. Again, we're going to be reviewing conic sections in a second. Anyway, the final thing is that this is a hyperbola, and since the y group comes first, it opens up and down. So you're not going to draw in this left and right version. You're only going to draw in the up and down version. And so that's what the hyperbola looks like. None of the, well, it shouldn't ever get further away from the asymptote. It needs to get closer and closer, right? But anyway, none of the asymptotes or anything are actually part of the graph. It's only the curves going up and down that are part of the hyperbola. Anyway, so that's that one. So that's how we can eliminate parameters to graph some of these parametric curves. But what if you wanted to go the other way around, right? What if you wanted to take a curve that is already given in rectangular form and you wanted to introduce a parameter to it in order to get a parameter equation or a parametric equation? Well, that's actually really easy, right? So to go the other way around, to introduce a parameter, all we have to do is realize that if y equals f of x, then x equals t and y equals f of t does the trick, right? For example, if f of x is x to the fifth plus x plus 1, then if you wanted to turn this into a parametric equation, all you have to do is say, well, let x be t, and then let y be t to the fifth plus t plus 1, and then that's a parameterization of f of x. So there's really nothing to that, right? Going the other way around is really simple. That said, maybe I should point out that there are infinitely many ways to parameterize a curve, right? This is just one of them. Okay. Anyway, so next question is, okay, so we probably want to be able to do some calculus on these kinds of things, right? So let's talk about the most basic one, derivatives, right? So how do derivatives of parametric equations work? Well, if you want to differentiate y with respect to x, what you could do is differentiate y with respect to t, and then differentiate x with respect to t. In other words, you can just differentiate, if you're given some kind of parametric equation like this, you can just differentiate each one individually, and that gives you the derivative of the parametric function, right? So it's really straightforward. The way that I said it may not sound very straightforward, but it'll become clear to you when we look at an example. So let's do an example, right? So let's say, for example, that we were tasked with finding the slope of the tangent line to the unit circle at the point where t equals pi over 6. Well, how would we do that? Well, we would just take the derivative of each one of those parametric equations individually, right? So we would just say, all right, so since x equals cosine t and y equals sine t, so then dx dt is negative sine t, and dy dt is cosine t. And so dy dx is just dy dt over dx dt. And that's just cosine t over negative sine t. And if you want, you could simplify that. Cosine over sine is cotangent, right? So this would be negative cotangent t, if you like. Of course, we're supposed to figure out what the slope of the tangent line is when t equals pi over 6. So at this point, we just plug in pi over 6. It's actually easier for me to think about plugging it in here, right? Cosine pi over 6 should be root 3 over 2. Sine of pi over 6 should be 1/2. So that would just be root 3, right? Or I guess negative root 3. So we would say dy dx evaluated at t equals pi over 6 equals negative cotangent of pi over 6. Whoops, sorry. And that equals negative root 3. Okay, that's that. A couple things to say about this, though, right? So since dy dx is just dy dt over dx dt, we'll get a horizontal tangent line whenever dy dt equals 0, right? So whenever the numerator is 0 and the denominator is not 0, we get a horizontal tangent line. So when dy dt equals 0, but dx dt does not equal 0. If dx dt does equal 0, then there are two possibilities, right? If dx dt equals 0 and dy dt does not equal 0, then in this case the tangent line is vertical. But if dx dt and dy dt are both 0, then actually we get something that's an indeterminate form. And so we call those points singular points, right? So points where dx dt and dy dt are both 0 are called singular points. And we can't really tell what's going on there in general. We have to analyze those cases on a case-by-case basis. Okay? So, okay. So let's look at a couple examples to kind of illustrate those points. So number 4 here says, a paper airplane follows the trajectory in example 1. This bad boy, right? So this is the flight of the paper airplane. Okay, for t greater than 0, but it crashes into a wall at time t equals 10. So like the edge of the page, I guess, is the wall, and it crashes at time t equals 10. Okay. At what time was the airplane flying horizontally, And at what time was it flying vertically? Well, I'm probably going to refer back to this graph once we get the answers to see if it makes sense with the way it looks. Because to me, it looks like it's flying horizontally, maybe here and maybe somewhere up here. I don't know. We might get multiple solutions. Vertically, it looks like it's flying vertically, maybe like here and somewhere over here and somewhere over here. But we'll see. So let's do it. Okay. So in order to determine where this thing is flying horizontally, it's going to be flying horizontally. So remember, dy dx is dy dt over dx dt. So it's going to be flying horizontally whenever dy dt equals 0, assuming that dx dt does not also equal 0 at that point. In this case, I don't think we're going to run into any trouble. And then it's going to be flying vertically whenever dx dt equals 0, assuming that dy dt does not also equal 0 at that point, which again, we're probably not going to have any issues. So let's just figure out what dy dt is then, right? So so for part A, right? So for part A, where we're supposed to try to figure out where the airplane is flying horizontally, or at what time the airplane is flying horizontally. So to figure that out, we're going to say, well, we need for dy dt to equal 0. So dy dt is going to be what? It's going to be 3 sine t. And we'll say this thing equals 0 if and only if sine t equals 0. And when does sine t equal 0? Sine t equals 0 whenever t equals 0. So t could equal 0, pi, 2 pi, 3 pi, 4 pi, and so forth. Of course, t has to be between 0 and 10, right? This is the paper plane crashes into the wall at time t equals 10. So I think 4 pi is bigger than 10. 3 pi is 3 times like 3.14. Ooh, that might be a close call. Let's see. 3 pi. 3 pi is like 9.4. So 3 pi also works. Okay, so we're going to scratch off the 4 pi and everything after it, but those are all good possible solutions. Now let's see, because we need to make sure that dx dt is not also equal to 0 at any of these points. So let's figure out what dx dt is. Right, because if dx dt is also 0, like let's say that dx dt is also 0 at 0, well then you don't have a horizontal tangent line there. What you have is a singular point, right? So let's see what dx dt is. Dx dt would be 1 minus 3 cosine t. Well, if I plug in 0, I get 1 cosine 0 is 1, so 1 minus 3, that's like negative 2, so that's not a problem. If I plug in pi, cosine pi is negative 1, so I would get 4, right? Here I would get negative 2 again, and here I would get 4 again. Okay, so no issues. So that's supposedly where the airplane is flying horizontally. So at time t equals 0, well, that's not really fair, right? Like that's the starting point. So it's not really fair to say that it's flying horizontally. I guess it takes off and momentarily it's like going kind of horizontal, but then it immediately picks up. At time pi, that's like 3.14. So somewhere between t equals 3 and t equals 4. So 1, 2, 3, 4. So somewhere between these two, Really? Oh, 1, 2, 3, 4. Got it. Yes, that makes more sense. So somewhere between these 2 points in time, it's flying horizontally, right, at about 3.14. At 6.28. So 1, 2, 3, 4, 5, 6, and 7. So somewhere between these 2 points, it's flying horizontally, right? Somewhere in between, and so forth. So this is making plenty of sense. And then it's flying horizontally again at like 9 point whatever, right? Somewhere out here, flying horizontally. So yeah, so that lines up with our picture, I think, pretty well. Okay, so we might as well answer part B then. And I've already done part of the work, because for part B, we want to figure out where the thing is flying vertically. And it's flying vertically whenever dx dt is equal to 0, assuming that dy dt is not equal to 0 at the same point. So, so we need this thing to equal 0. That's going to happen if and only if cosine t equals, well, I subtract the 1 and then divide by the negative 3 and get a positive 1/3, right? Ugh, that's nasty, but, you know, what are you going to do? So what are we going to get? T equals cosine inverse of 1/3 plus 2n pi, right? That's all of the possible solutions that we get from that particular one. But then there's another possibility that t could be 2 pi minus cosine inverse of 1/3 plus 2n pi. Okay, so these both are going to generate a bunch of solutions. Let me just approximate them to see about how much these things are. So cosine inverse of 1/3 is about 1.2. And if I add 2 pi, I get 7.5. And if I add 2 pi again, I'm at like 13.8. But that's already too big because t has to be, you know, less than or equal to 10. Okay, what about this other one? So 2 pi minus cosine inverse of 1/3 is about 5.1-ish. And then if I add 2 pi, I get like 11.3-ish, which is already too big. Okay, so it looks like those are my 3 possible solutions. So the exact value here is cosine inverse of, so this is cosine inverse of 1/3. This one is cosine inverse of 1/3 plus 2 pi. And this one is cosine inverse of 1/3, actually it's 2 pi minus cosine inverse of 1/3. So those are my three solutions. But the approximations are better in terms of like when you're looking at the graph, right? So let's see if it makes sense, right? So when t equals 1.2, so 1, 2, so somewhere in between, right? You're flying vertical. Okay, makes sense. 7.5. 1, 2, 3, 4, 5, 6, 7, and 8. So somewhere in between here, you're flying vertical. Makes sense. And then 5.1. 1, 2, 3, 4, 5, 6. So somewhere between 5 and 6. I mean, I didn't draw the graph very well, I guess, but you know, but it makes some sense, right? That you're flying vertical at those places. So there you go. Okay, let's look at another problem. It says, consider the semi-cubical parabola, which, by the way, before preparing this lecture, I had no idea that there was such a thing as something called a semi-cubical parabola. But your book, you know, has this example in it. I thought it was a good one. So consider the semi-cubical parabola, x equals t squared, y equals t cubed. And here t could be anything from negative infinity to positive infinity. Part A asks us to graph this thing by eliminating the parameter. Excuse me. And then part B says to compute dy dx and d squared y dx squared. So first and second derivatives at these points. Oh, and it wants us to do so without eliminating the parameter. Okay, fine. All right, so we've got x equals t squared, y equals t cubed. So we want to graph it. So first of all, they want us to graph it by eliminating the parameter. Well, So we could do our old trick of like solving for t. Man, and see now the tricky part with that though is that if you take the square root to solve for t, you're going to get t equals plus or minus x, right? So you're going to get two possible solutions, and then that gets messy. You can solve for t here and plug it in there, but there are three solutions here, right? Of course, the other two are, well, yeah, I mean, if t is a real number, you're only going to get one real solution out of that. The other two would be complex. So I suppose that might be okay, actually. You could call this cube root and then plug it in there. Yeah, let's do that. Your book takes a different approach, but I think that's fine. We can say, I'll show you the approach your book takes. Let's do it the way your book does it, and then I'll show you what I was thinking. So the way your book does it is it says, well, if you cube this one and square that one, then you get t to the sixth in both cases, right? So you get x cubed equals t to the sixth, and y squared equals t to the sixth. Since x cubed and y squared equal the same thing, they must be equal to each other, right? Therefore, x cubed equals y squared. And there you go, you've eliminated the parameter. I'll admit that's kind of a slick way to do it. I'm not sure I would have thought of it myself. I probably would have thought like, okay, so t equals the cube root of y. And then I would have said, okay, so then x equals t squared. So it would be cube root of y squared. Or in other words, x equals y to the 2/3. And if you're thinking, well, that doesn't look anything like that. Well, it does, really. You take the cube root of both sides here, and you get x equals y to the 2/3. Or you could take the square root, and you could get y equals plus or minus x to the 3/2, which is kind of a nicer way to do it. Here you could do the same thing. Cube both sides, then take the square root, and you'll end up at the same spot. Y equals plus or minus x to the 3/2. Anyway, in terms of being able to graph it, this is really the best way, I think, to think about it. Because, we have some idea of what x to the 3/2 looks like. I mean, the exponent is bigger than 1, so it sort of looks like a parabola. Right? So without getting super specific, I mean, y equals positive x to the 3/2 is going to look like that, and then y equals negative x to the 3/2 is going to look like that, right? So that's what this thing looks like. So there's part A. And then part B asks us to find the first and second derivatives at these points, at 1, 1, and at 1, -1. Okay. No problem, right? So we want dy dx. Well, that's just dy dt over dx dt. So dy dt is 3t squared. Dx dt is 2t. So I guess that would just be 3/2 times t, which is pretty nice. D squared y over dx squared then is just, well, for that I'm just going to say it's the derivative of 3/2 t, right, which is just 3/2. So there's the second derivative. Boy, did I make a mistake somewhere? So dy dt is 3t squared, dx dt is 2t. Yeah, that should be correct. Okay, I think I'm good. I just wasn't expecting to get a constant for the second derivative. That's okay. The reason I wasn't expecting to get a constant is because they want us to evaluate these derivatives at specific places. They want us to find these derivatives at the point 1, 1 and 1, -1. Now here we have a problem because these coordinates are given in xy, xy, and this derivative is given in t. So we need to figure out what t corresponds to the point 1, 1 and 1, -1. So at 1, 1, well, if we look back at our original functions, our parametric functions x equals t squared, y equals t cubed, when t equals 1, you get x equals 1 and y equals 1. So at 1, 1, t clearly equals 1. And at 1, -1, well, if you plug in -1, -1 squared is +1, -1 cubed is -1. So t should be -1. Okay? So dy dx evaluated at 1, 1 should just equal dy dx evaluated at t equals 1, which is 3/2 times 1, which is 3/2. And dy dx evaluated at 1, -1 should equal dy dx evaluated at t equals -1. That's 3/2 times -1, which is -3/2. And so there are the first derivatives. As for the second derivatives, well, the second derivative was just a constant 3/2, right? So d squared y dx squared evaluated at 1, 1 is just 3/2. And d squared y dx squared evaluated at 1, -1 is also just 3/2. Okay? Okay, so that's that. Notice that at 0, so at the point 0, 0, by the way, that would happen when t equals 0, dy dt equals 0, and dx dt equals 0. So you get that indeterminate. And so as you can see, at this point right here, you don't have a vertical or a horizontal tangent line. What you have is a singular point, right? That's a singular point. And it's a singular point because dy dt and dx dt are both 0 when t equals 0. At t equals 0. Okay? Anyway, so that's just something that is worth pointing out. Okay, one last concept. How long have I been talking? We've been going for almost 50 minutes. So yeah, so we need to get to the end here. But there's one more concept real quick, and it's the arc length. So the arc length of a parametric curve. If no segment of the curve represented by this parametric equation is traced out more than once on this interval, and if dx dt and dy dt are both continuous on the interval, then the arc length L of the curve is L equals the integral from a to b of the square root of dx dt squared plus dy dt squared. This is really similar to the arc length formula we had before when we were working with one dimension, where we had, integral from a to b of square root of 1 plus dx dt squared, or whatever it was. Integral from a to b is square root of 1 plus, whatever. Anyway, so this is a similar type of formula. So let's practice applying it, and then this is our last example. Okay. So it says, use the arc length formula to derive the formula for the circumference of a circle of radius r using the parametric equations here. Okay. So let's do it. Okay, hold on. All right, sorry. Okay, so let's do this thing. So we want to use the arc length formula to derive the formula for the circumference of a circle, right? Because what is the circumference? It's just the arc length of the entire circle, right? So it's just an arc length thing. So we're going to integrate from 0 to 2 pi the square root of dx dt squared plus dy dt squared, and that's really all there is to it. So let's do that. So it's the integral from 0 to 2 pi of the square root of, well, what is dx dt? Dx dt is going to be negative r sine t. So there's dx dt squared plus dy dt. What's dy dt? It's going to be r cosine t squared. Okay, and that's all there is to that. So what do we get? Well, this is just going to be r squared sine squared t, and this is going to be r squared cosine squared t. We can factor out the r squared. And wouldn't you know it, right? Sine squared t plus cosine squared t is just 1. Square root of r squared is just r. Well, really the absolute value of r, but we're assuming that r is a radius, so it's a distance, so it's going to be positive anyway. So we just have r, which we can take out of the integral altogether, and then dt. How boring, right? This is just r times t evaluated from 0 to 2 pi. That's going to be r times 2 pi minus r times 0, which is just 2 pi times r. So the circumference of a circle is 2 pi times r. As you've always known, but hey, now you've proven it, right? Now you're able to prove it. Okay, that's that.